All right, so we're moving on from major entities to look at a few more qualitative analysis ideas, and then a couple more little things like energy and naming acids, which is totally review. This is a little bit different than what you're going to see on your notes page, but it is the exact same information. So just the difference between qualitative versus quantitative. Qualitative means we are determining what is present based on properties and observations. So things like our solution color, flame color, precipitation reactions we talk about a little bit later, litmus and conductivity. They're all kind of a yes or a no test. All right. Quantitative, however, is determining how much is present, and it's based on measurements. So we're actually going to have numbers. Looking at pH or stoichiometric methods, which is our next unit. So colorimetry, the way we get solution color, is kind of interesting. It's that different ions absorb specific wavelengths. So it's actually that they absorb that wavelength, not that they emit it. This makes analysis possible. So we are looking at the fact that on the wavelength spectrum, with different wavelength has different colors. So a specific color can identify an ion. The strength of the color tells us how many ions present or the concentration of that solution. The color can depend on an element's charge. So looking at the back of your periodic table, you'll find colors of solutions or ion colors. It's not the exact same table, but it's very similar. Just note that copper 2 plus and copper 1 plus actually have different colors. So dependent on the charge of the ion, like I said, we're going to see some different colors sometimes. If it's not listed, it means that it is colorless. Flame colors, so when I burn an element, some of them emit different colors. So if you've gone and had a campfire and bought one of those packets of like rainbow campfire or whatever, it's actually just different elements. So you should never roast your marshmallows over it. Anywho, the reason that this happens is that metal ions emit different spectra or wavelength when they're heated. So what happens is that electrons are typically going around in their certain wavelength or their certain circles. When it absorbs heat from the flame, the electron jumps to an outer wavelength level. So they have lots of energy. They're able to keep going around in that bigger level until it cools down. What happens is it falls back down to its original level and it emits energy in the form of light with different colors as it does so. So flame colors, are listed on the back of your periodic table as well. Diagnostic tests are used to determine properties of a solution or to identify a particular substance. So this is right back to where we are on your booklet. That was just kind of the interlude in the background. The conductivity test we know is used to test for electrolytes, and the litmus test is used to determine if a solution is acidic, basic, or neutral. The color of a solution can identify ions, and it's on the back of your period. So let's go ahead and use our periodic table to answer the following questions. Sodium chloride is mixed in water and sprayed into a flame. What are the colors of the solution and the flame? So what we're going to do is we're going to find our major entities, and we're going to look on the back of the periodic table, and we're going to find the colors. So sodium chloride mixed in water, we're going to get Na plus AQ and Cl minus AQ. So looking at our solution colors, doesn't matter what concentration we're looking at, we can see that sodium is not listed, nor is chlorine, meaning that our solution color is colorless. The flame color, we're looking at table G9 on the back of your periodic table. And I can see that sodium is listed, and sodium has a yellow flame color. Chlorine's not listed, so it would have a colorless flame color. So we're actually just going to be seeing sodiums. Going through this again, potassium hydroxide mixed in water, so AQ on each of these. Sprayed into a flame. What are the colors of the solution and the flame? Well, potassium and hydroxide are not in our ion colors, table G8. So the solution is again colorless. However, we do see potassium. In our flame colors, it is violet or purple. Hydroxide isn't there, so it would be clear in both cases. Strontium bromide, so Sr2 plus AQ and Br minus AQ. Mixed in water, sprayed into a flame. What are the colors of the solution? Well, strontium doesn't have a color, nor does bromine. Therefore, it is colorless. Colorless. And the flame color, we find strontium, not bromine. So bromine would be colorless. Strontium is red. Last one, potassium permanganate is mixed in water. Remember, any group 1 ion is aqueous, or soluble, sorry. So this one will be aqueous. And we have MnO4 minus. K plus is not located in our solution colors. However, MnO4 is. MnO4 is permanganate, and it is a deep purple. The flame color, permanganate isn't listed in our flame colors, but potassium is, and again, it will be violet. So using those two tables, we could identify different compounds in solution, or we could identify different compounds by flame color. All right, moving on, we are looking at energy changes in solution. So that means energy as we are dissolving things. It's difficult to predict whether the dissolving of a solute will be exothermic or endothermic before actually attempting it, because we can only observe the effects of the surroundings. And the surroundings in this case would be the water that we're dissolving it in. Water in the beaker. So we can feel if it heats up or if it cools down, but that's about it. So remember, exothermic means that energy is released. And endothermic means that energy is required or absorbed. So this is where our solution will get cold because the bonds are taking in energy. And when it's released, we're going to feel heat. So the dissolving of a substance is a physical change. We could reverse it by just evaporating things, where the bonds of the solute are broken to produce ions or molecules. So we're either breaking intra for ionic or intermolecular forces for molecules. So that's like hydrogen bonding, dipole-dipole attractions, and London dispersion. The solute molecules or ions then become attracted to the solvent particles, which typically is going to be water. Remember, it's polar, so we can have positive and negative attractions here. We know in chemistry that breaking bonds requires energy, or that energy must be absorbed to break a bond. So if we're breaking bonds, energy is absorbed, and things might feel cold. So we could break ionic bonds in the solid, or the intermolecular forces between molecules like I was talking about earlier. I'm going to skip ahead here. We know that breaking bonds requires energy, but forming new bonds actually releases energy, so it is exothermic. Electrostatic forces between ions and water molecules form, and those are the new forces. So we call this ion dipole attractions. So a positive or a negative is attracted to a polar molecule. The overall energy change in the dissolving process is the net sum of the energy absorbed and released. If more energy is released in the formation of new bonds than is required to break the original bonds, the overall process is considered exothermic. If less energy is released than was required to break the initial bonds, then overall the process is endothermic and has required energy. So, an example, you might want to write this down somewhere in your pages. Sodium hydroxide is dissolved in water and the beaker gets hot. What's up with that? So we need to talk about all the different energy changes happening. We know that breaking the solute-solute bonds, or the ionic bonds within NaOH, requires energy. This is an endothermic process, so it's going to first take in energy from our water, making our water slightly cold. It's also got to break the solvent-solvent bonds. We have to break bonds, hydrogen bonds between water molecules, which also requires energy. We need to break these because we're actually going to put some ions in between some of them, and so we've broken those hydrogen bonds. We form new solvent bonds with ion dipole attractions between anions in water and cations in water. This releases energy. Overall, we know that the water is heated up. Okay, so we know that lots of heat has been given off. Therefore, this process is huge, and these ones are really little. So it takes a little and it gives off a lot of energy. More energy was released in forming those new bonds than was required in breaking the initial bonds. Therefore, this process is exothermic overall. All right, last little step. This is review, guys. You should remember this. Two systems for naming acids. IUPAC nomenclature names the acid as though it were an ionic compound and adds aqueous in front of it. And the classical system is something we've reviewed. If it was if it was hydrogen something ide, so this was our binary, it becomes hydro something ic acid. If it ended in ate, as it was a polyatomic, we would get ic acid, and if it was another poly and it ended in ate, it's OUS acid. So some examples. You guys should stop this. You should pause it right now, and you should attempt these on your own and then use my work to check yours. So all of these are going to start with aqueous, but I'm going to run out of room, so I'm going to abbreviate AQ, hydrogen chloride. Okay, AQ, hydrogen nitrate. AQ, hydrogen. Now, because this isn't a polyatomic, remember, just like ide in endings for ionic, we have iodide. Aqueous, hydrogen sulfate, and aqueous hydrogen sulfite. Now we can see the endings, so this should make our job fairly easy in classical naming. Ide becomes hydrochloric acid. Ate becomes nitric acid. Ide becomes iodic acid. Hydro. Sulfate becomes sulfuric acid, and sulfite becomes sulfurous acid. All right, so there's not a lot of homework for this. You really do need to review that energy changes and understand the processes. So like I listed out for the NaOH, you do need to know that for both an exothermic and an endothermic. So maybe use that as some practice. For tomorrow, you're doing a solutions lab, so be sure you're wearing appropriate footwear. What you're going to do to prepare for this lab is complete the prediction and procedure of the lab handout using the qualitative tests we have discussed thus far. We are not using flame colors this time. Sorry, guys. I'll do a demo sometime after the break for you. Wednesday after the break, you're going to have a solutions quiz. This is up to the end of the information presented in this video.